Hi everyone. We are doing our States of Matter test review today. Excuse my appearance, it's been a very long day. I'm recording this on Tuesday. Honor section, you're watching it on Wednesday. Regular section, you're watching it on Thursday. This is a one-size-fits-all sort of test review. Even though my honor section did do a little bit more, I'll kind of give you the heads up. Regular sections, that's my 12:30, my 2:30 class, when you guys can tune out, because we did a little bit more with honors than you guys had to do. But you're all taking the test this week in my absence, so I want to definitely help to prepare you for that. So before I get started, there was a worksheet that goes along with this. It's in Doc Sharing. It's embedded in the course, and hopefully I K-mailed it to you. I wanted you to try to work on that yourself based on what you already know and or reading through the course, and really use this session as an answer key sort of explanation for maybe things you weren't sure about or things you need to work on more, things you were totally lost on. What I don't want you to do is get your worksheet now and just start filling it in. The assignment's worth 10 points and it is required, but it defeats the purpose of a review if you're just gonna copy it along the way. Obviously, I can't really be as interactive here as I can in the course when we're live for a review like this. As you've seen with some of my other lessons this week, I can make these recordings interactive, but with a review like this, I have question after question after question, and it would just be constant. And really, that's the same thing as you actually filling out the worksheet. So I am just going to approach this session as going through it, explaining along the way, answering what I can, and hopefully, as I said, you can double check your answers or maybe gain some understanding where you didn't have it before. Okay, so let's recap. What did we do in the States of Matter unit? Well, the big idea we said was changes in matter are accompanied by changes in energy. And for everyone, you should have been able to see that in the kinetic molecular theory that we studied, all talking about how molecules move when we change conditions like temperature or pressure. Understanding specifically when we change one property, how does another one get affected? And of course, that's contained in Boyle's, Charles, and Gay-Lussac's law, as well as the ideal gas law, once we sort of understood what an ideal gas is. We talked about how molecules collide, gas molecules specifically, how they collide, and looked at the molecular structure of gases. Now, if you're in my honors section, you additionally looked at Graham's law of effusion and how the rate of diffusion of gases changed with the size of the molecule, the molecular weight. You also looked at phase diagrams and how to interpret them, how to read them, how to determine what temperatures and pressures to change in order to get the phase that you want. We've talked about and studied the molecular nature of solids, liquids, and gases, how they're different, how they're the same. And then finally, some properties of liquids and solids that sort of are an afterthought because gases are so important. And with that, I'm basically going to go through lesson by lesson, just like with exactly what you guys have for your worksheet as your review for this test. Starting with lesson 1. You'll recall way back, lesson 1 was just a behavior of gases lesson. It was what's going on in gases, what are their properties, very overview. And so working through that here, question 1 says match the following descriptions to the correct state of matter. Do we have a solid, a liquid, or a gas? And so we'll go through and just mark those here. A says has no definite shape or volume. So no definite shape rules out solid, right? A penny is a penny is a penny is a penny. It's always a circle and it's always pretty flat. That has a definite shape. Liquids, however, take the shape of their container. Drinking a lot of this week. And gases take the shape of their container. But gases will escape if we take the lid off, and liquids will not. We crack the top open on a can of soda and they don't escape because there's only a finite volume in there. Right now there's only a tiny bit left. So definite volume means It takes up a certain amount of space. Gases, however, if I had gas in here, open the container, it would fill the room. There would be tons of empty space between those molecules, but it wouldn't be a definite volume. So your answer to A is going to be C. This is a gas, for sure. No definite shape or volume. Gas is the wild child. Fills the space of its container. And we're saying fills, not just takes the shape of. When we say it fills, it means if we take the top off, it will escape. Again, that is letter C. I'm pretty sure that these are the exact same questions I asked you at the beginning of our lesson 1 lesson. Has a definite shape and volume. Definite shape is always our solids. A penny is shaped like a penny all the time, unless we hammer it to death, right? Does not fill the space of its container. That could be a solid or a liquid, right? Because a gas is the only one that actually fills the space of its container. So I would take there either A or B. And then has no definite shape but has a definite volume. That's an example of our liquids. So the liquid always takes the shape of its container, whatever cup or mug or bucket or pail or bathtub that you fill water with, it's going to take the shape of that container. Right? So it's not a definite shape. It takes the shape of its container, but it does have a definite volume. If you're a half full or half empty glass person, doesn't really matter. Half is a half is a half, right? It doesn't exceed it, doesn't fill it. So it has a definite volume. And finally, again, fills the space of its container is a little bit of a repeat because we had that up here in problem B, my error. This was sort of basics. What's the difference between each phase of matter? Then we talked about specifically properties of gases. What are the 5 properties of gases discussed in this lesson? And of course, we tried to give you a word bank to work with. We talked in this lesson about diffusion, volume, pressure, which we went on to discuss at great length in this unit. Expanding and compressing, those are 2 opposites, right? So let's see where they fit in here. Number 1 says gases blank as more molecules are added to a container. And the correct answer there is expand. Let me see if I can write that small enough. Expand. Gases expand. What do we mean by that? We blow air into a balloon, the balloon grows. Okay? Gases exert pressure. So we use expand. Gases exert pressure like in the tires of your car. And you need to measure that pressure in order to make sure that they are filled properly. Gases exerting pressure is also, we're talking about fundamentally the molecules hitting the sides of the container, hitting each other. That's pressure. Just like if they say put pressure on a wound if you get hurt and you can squeeze it and it feels better, or maybe you get sliced and you're bleeding and you put pressure on that wound, it won't bleed as much because you're sort of blocking the flow of blood in your veins and your arteries. Pressure is a push. It's a force. And so that's exactly what we found that gas molecules do. Number 3 says gases are blank. Their volume decreases as their pressure increases. Their volume decreases as pressure increases. So we're putting force on that balloon and the volume is decreasing. This is a phenomenon called compressibility. You can compress gases. Anybody ever hear of compressed air? So you can buy those little cans, to spray the dust off your computer. That's compressed air. An air compressor that you might see in a garage or definitely in like a mechanic's garage is useful for a variety of things like filling car tires with air. That's because gases are compressible. We can fill a lot of gas in a small space. Number 4 says the blank of a gas changes with temperature. That answer is volume. Hopefully that's one that sticks. That's Charles' law. We did our lab on that one. If we put the balloon in a hot water bath, the balloon grows, albeit very small. And if we put it in a freezer, it shrinks. Number 5 says gases diffuse And again, for those of you who are not in my honor section, we didn't talk a great deal about this, but it's important that we know what it means. Diffusion means that they travel from an area of high concentration to an area of low concentration. That's definitely a vocabulary word you need to be familiar with. And for those of you in my honor section, of course, you know we spent a whole day on it, an entire lesson, and so you want to know the specifics about that going forward. Okay, pressure specifically has like 6 or 7 different units we can use to describe it. So the question here is, which of the following represents units of pressure? Because a lot of times when we're solving these problems, we need to be able to pull out of the text problem what's what, right? Assign our variables, and it's our units that allow us to do that. So if we know, of course, that atmospheres is a pressure measurement, that's a great thing. Of course, Celsius is temperature, so we would rule that one out. Liters is a volume measurement, and that's something we should know in this unit in particular because we use a lot of volume variables. Pascals, we said, is that very common scientific unit. You'll see when we get into, I'm pretty sure we use pascals when we talk about thermodynamics and heat exchange, I think. Pounds per square inch is what we use to measure the pressure in our car tires. So that's more of a practical pressure measurement. Just like ATMs, atmospheres, of course, the word itself sort of lends itself to an environmental application. And then Kelvin, of course, is also temperature. So we have pressure, 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 2 temperatures, and a volume. Still in lesson 1, talking about behaviors of gases, what does STP stand for? We haven't visited this in a while, but we learned this originally in our stoichiometry unit when we learned molar volume, and we revisited it here because, why do we do that? Oh, I think we were just saying we need things at STP because volumes change when we change temperature. So STP stands for A, standard temperature and pressure. And those units in Kelvin and kilopascals are 100 kilopascals and 273 Kelvin. Now, of course, you may have learned this and committed to memory in the stoichiometry unit that was equal to 0 degrees C. But you'll recall that the conversion from Celsius to Kelvin is to add 273. So that's something you're going to be responsible for on this unit test, is knowing that conversion. And also, I believe 100 kilopascals is equal to 1 atmosphere. So just know that standard temperature and pressure is characterized by a certain set of conditions, but the units on those conditions don't have to be, it doesn't have to be expressed in Kelvin, doesn't have to be expressed in kilopascals. These things are exactly equivalent. Okay? All right, this is probably something that you looked at and you went, what? She needs me to know that? Oh, lessons 2, 3, and 4, we spent talking about Mr. Boyle, Mr. Charles, and Mr. Gay-Lussac. And when we did that, we categorized the relationship between variables as either direct or indirect. And in every lesson, we introduced a new law. We showed you the graph and how that would go, the graph of volume versus temperature or volume versus pressure. And that's what we have here. So I've asked you to label these graphs as direct or indirect, because this is something you need to know going forward, really. So I want to take you through an actual reasoning to this before I give you the answers. You should look at chart A and B and look at what happens to the temperature or the pressure, to the temperature or the volume, or either of these variables as we increase. So of course, this is increasing temperature, right? And this is increasing volume. So if we pick some random points on this line, and we say point 1, 2, and 3. Well, at point 1, relatively speaking, we have a low temperature, right? And that temperature corresponds with a relatively low volume. And point 2 is a much higher temperature, something halfway between that scale. And it corresponds with a much higher volume. And number 3 goes even higher temperature and a higher volume. So in this case, the same effect happens to both. Okay, and in B, we look at pressure and volume. And of course, in the same way, pressure would increase as we go to the right, volume would increase as we go up. So picking our 3 points in the same way that we did before, I'm going to pick points 1, 2, and 3. We're going to see that point 1, relatively speaking, our pressure is low, it's on the low end, but our volume is high. And then if we change our pressure, and now the pressure is considerably higher than point 1, but our volume has dropped. And then with point 3, we have the highest of the 3 pressures and the lowest of the 3 volumes. So what has happened here is that the opposite effect has happened to both. So now it's a matter of knowing what's what and how this matches, how this works. When you have the same thing happening to both variables or both properties, we're talking about a direct relationship, and that is always characterized by a straight line. Okay? When you have 2 different things happening, we're looking at an indirect. Or the other words we have used is inversely proportional. An inverse or indirect relationship. Okay? And that again is always categorized by some curved line. Whether it goes to the left or to the right doesn't really matter as long as it's curvy. Okay? Now, knowing that they are direct and indirect, we do want to be able to match those circumstances to each of the laws. And this is really about just remembering what happens in every law. And we will sort of dissect this in the future. So as an introduction, I'm going to go ahead and just lay this out on the table. Boyle's law, and I'm not really sure. Whoops. Sorry, things are going kind of crazy for me here. Hmm. Okay, there we go. I'm not sure what happened there. Okay, so we have our direct or our indirect scenario. Okay. Boyle's law. Now, as I was saying, sorry, I don't know how you would do this without knowing the equations. So I do, of course, know the equations pretty well. And Boyle's law is the P1V1 equals P2V2. In Charles' law, we're looking at V1 over T1 equals V2 over T2. And in Gay-Lussac, we're looking at P1 over T1 equals P2 over T2. So if you'll recall, I tried to give you a little mnemonic device for remembering this. Whenever you have division, you have direct relationships. Okay, so in Charles' law and Gay-Lussac's law, we're looking at a graph that is described by A above. Okay, when you have multiplication, it's different. Even though it seems a little bit more straightforward, maybe counterintuitive, that is an indirect or inverse relationship between pressure and volume. But we'll get the chance to look at these much more closely. This number 3 clarifies that a little bit. So we did just say if each one was direct or indirect. Now we're going to say what happens to the variables. So increase or decrease with each law. Part A says according to Boyle's law, when the pressure on a gas increases, the volume of the gas decreases. And why is that? Again, because Boyle's law is multiplication between pressure and volume. That means it is not direct, making it indirect. When it's indirect, we have that opposite opposite thing happening to both variables. So it would decrease if the other one increased. In B, it says, according to Charles' law, when the temperature of a gas increases, the volume of a gas also increases. Because as a direct relationship between volume and temperature, we have this straight line effect, whereas one goes up, so does the other one. And that's the same situation as we have in Gay-Lussac's law. These things need to be understood for the test. We're going to test you on them and test you on them and test you on them, because it's not just about the math. It's not just about the problem solving. There's huge concepts here that we viewed in real life applications, demonstrations, laboratory assignments, simulations. It should be something we understand. And so as a review, I would be remiss not to include it at length. Okay? We have a few examples here just to remind you what you're looking at for each of these laws. So over the course of the next 3 slides, we'll do one example from every lesson, 2, 3, and 4. And I'm just going to go ahead and straight up solve these. Again, you should be using your worksheet and this session as an answer key. Number 4 says use Boyle's law to solve the following problem. And we didn't give you Boyle's law equation here, so as soon as you see Boyle's law, you're going to write P1V1 equals P2V2, and you're going to go ahead and hopefully get ready to assign your variables. Okay? Question says a sample of oxygen gas at 295 kilopascals takes up 456 liters of space at standard temperature. What's the new volume when the pressure is lowered to standard pressure? And so we need to know standard temperature and standard pressure here. We said standard temperature in Kelvin is going to be 273. And it doesn't say that the temperature changed. So one aspect of Boyle's law is that we have constant temperature. And that's necessary to be true in order for this law to hold to what it is. Okay? But we need to know standard pressure, and we need to be able to match our units. So the first pressure gives us kilopascals. That means we need to know standard pressure in kilopascals. Okay? Our first pressure then, P1, is 295. Our first volume, 456. I'm going to get my calculator ready. Our second pressure is going to be only 100 kilopascals, and we don't know our new volume. Now I'm going to take a moment to just remind you that we can do this based on some rationale. So knowing that we have a indirect relationship between, an indirect relationship in Boyle's law between pressure and volume, we have opposite things happening to each. So if the pressure increases, volume decreases. Pressure decreases, volume increases. Here we have pressure pretty clearly decreasing. P decreases. So we can make some assumptions here, hypothesis. V will increase. It will do the opposite, right? So we should get an answer that is higher than 456 liters. And so that rules out A as an option. It also rules out B as an option. We're looking then at 1,120 liters or 1,335 liters. I'm going to go ahead and just substitute this into the equation, where we have 295 multiplied by 456 equals 100 times V2. Okay, doing that math real quickly, 295 times 456 is equal, oh, that's not right. 295 times 456 is 134,520 equals 100 V2. We have to divide both sides by 100, because that's how we do algebra, to solve for V2 or to solve for x. Dividing by 100 actually just moves our decimal point 2 places to the left. So our answer is 1345.2. And this is going to be in liters because those are our volume units. That is one of our options. That is the correct answer. And we've already eliminated to make sure that it will actually increase. So we found a number that increases, that follows with theory, it follows with the law, and it matches one of our answers that's there. So that's Boyle's law. Moving on now to Charles's law. Okay, Charles' law, and we have given you the equation here. You can expect on the test that we will give you the equations that you need because we're very generous like that, probably to a fault. Okay, V1 over T1 equals V2 over T2. A flexible container holds 2,003 cubic centimeters of air at a temperature of 285. What would the new volume be if the container were cooled to 18 degrees C? So what I've tried to do here is highlight, and you should do this too when you're working, like underline or highlight or box or circle, whatever. Separate your 1 and your 2. Remember, V1 is our initial volume. V2 would be our second volume. The other thing you want to do right away is check out your units. Make sure you have units of Kelvin if you're given temperatures. And so we did show you how to convert Kelvin here as well. A Kelvin temperature is merely 273 plus whatever Celsius temperature you have, which in this case is only 18. 291K will be our temperature here, and that's actually our first temperature. So looking at V1, T1, V2, and T2, our first volume is 203 cubic centimeters. Our first temperature is 285 K. We don't know our second volume yet. In our second temperature, we solved for 291. It said it cooled. That has to be wrong. I think the question must be wrong. Let me just double check my math. 18 plus 273, yes, 291. So somebody writing this question must have been not doing so good that day. This should say heated, because it wasn't cooled. We went from 285 to 291. That is an increase. That's not a decrease, right? T increases. Sorry if you can't really tell what that is. Now the variable we don't see here is P, and that's because pressure is constant when we're talking about Charles's law. Okay? If T increases, Charles's law, we come back up here, we said Charles's law, what happens to one happens to the other. It's categorized by this perfect little line, and so if we have T increasing, we can expect V to also increase. Okay, we're solving for V2 here, so that's a pretty easy variable to solve for if we just plug and chug. So I'm going to go ahead and do that. First volume is equal to 2003 divided by 285 equals V2 over 291. Okay, so on the left, I go 2003 divided by 285. That works out to 7.02. And I have my V2 over 291. Now I'm going to multiply both sides by 291 so that I cancel it on the right. And I'm left with V2 on the right, solving just for that. Multiplying that by my 7.02, we get an answer that is 2,045. And of course, this is going to be centimeters cubed, not liters. So be careful of that. Now, I did this whole thing. I did this hypothesizing, and I never eliminated some answers. So if we expected V to increase from 2003, that means we would eliminate option A. It's less than 2003. We'd eliminate option B because it's less than 2003. We'd eliminate 2003 because it's the same as 2003, and then actually by process of elimination we get C, 2042, but it also happens to match the answer we got, off by a few single-digit units, and that's no big deal. Okay? Pretty straightforward stuff. We've done it over and over and over again. In number 6, we're looking at using Gay-Lussac's law to solve a problem where we have constant volume. And we know it's constant volume because there's no volume in the equation. It's just changing P, 1 and 2, changing temperature, 1 and 2. Okay? At 195 degrees C, the pressure exerted by oxygen is 745 kilopascals. What will be the pressure at 568 Kelvin, assuming constant volume? And of course we do have degrees C here, so we're going to have to play with that a little bit. And actually, let's convert that right away. Our 195 plus 273 is going to equal something pretty big, huh? It's a high Celsius temperature, 468 Kelvin. And then we increase to 568. So let's write our equation. Let's set this all up. P1, T1, P2, and T2. Our first pressure is 754 kilopascals. First temperature we solved for 468 Kelvin. Second pressure we don't know. And second temperature is 568 Kelvin. So again, we're doing Gay-Lussac's law. Gay-Lussac's law is so similar to Charles's law. We said up here that Gay-Lussac's law is a direct relationship, and that means that if the temperature increases, then the pressure must also increase. And that's exactly the scenario we have in this example. We have temperature increasing by 100 units from 468 to 568. If the temperature increases, we can expect P to increase as well. Okay? So if pressure is going to increase from the original 754, that means we can't have 352 be the right answer. That's less than 754. C is also not the right answer. That is less than 754. We're left with 915 or 2,196. And we have to do the math to determine between those two. So let's plug and chug here. First pressure is 754 divided by 468 equals P2 divided by 568. Okay? And you can either multiply by this 568 now or later. Just to change it up here a little bit, I'm going to multiply it now. So just to be real clear about how this math is done, you can do order of operations and do that division first and then multiply, or you can go ahead and just tack it onto the numerator. Both of them are equivalently correct. Okay, this is a calculator problem, 568 times 754. Big number divided by 468, I get 915. And this is pressure. We're using kilopascals in number 1, so our final units are in kilopascals. Okay? The pressure did increase, only slightly. Okay, if I'm going a little quick, understand that it's because you can pause this recording at any time. Rewind, fast forward, do what you need to do. I'm already 34 minutes in and I'm only not even halfway through the unit. So I have to continue chugging along. We skipped from lesson 4. Somewhere in there we did a lab and I don't think there was any other lessons. But we skipped in number order all the way to lesson 10 in this unit, where we talked then about, after the individual gas laws, we talked about the combined gas law and the ideal gas law in one lesson. So just a reminder, there's an equation or a gas law which allows us to determine a new volume new temperature, so should say new volume, new temperature, and new pressure of a gas after a change from the initial volume, temperature, and pressure. This gas law is called the combined gas law. And its equation goes like this. P1 V1 over T1. So that's a combination of Boyle's law on the top, Charles' law here in the volume and temperature, and Gay-Lussac's law on the pressure and temperature equals P2 V2 over T2. Combined melds together Boyle's, Charles, and Gay-Lussac. It allows us to have initial conditions and final conditions of every single variable. Nothing is held constant. Okay. But there's only one gas law that allows us to calculate the amount of gas present in a sample, usually by determining how many moles, when we know volume, temperature, and pressure. The name of that gas law is the ideal gas law. And its equation goes something like this. PV equals NR and T. We don't have an initial state here. We don't have a final state. We just have a pressure, volume, and temperature, and then our number of moles and a new unit, a new number, if you will, and that is R. R is our gas constant. Gas constant has two different units, right? Liter ATM, Kelvin mole, or liter kilopascal, Kelvin mole. And the number we use depends on what pressure we're given in the problem. Part C here says which variable in the equation would we solve for if we're solving for the amount. And of course that would be N. It equals number of moles. This is the only equation where we can determine how much gas is there. Nothing is assumed constant here because nothing is changing, or nothing is assumed to be changing. Everything is assumed to be constant. Okay? So looking at a quick example of ideal gas law, because the combined gas law is just more practice of our original ones, really. It says a tank with a volume of 348 milliliters contains 1.5 moles of neon gas. The maximum safe pressure the tank can withstand is 450 kilopascals. At what temperature will the tank reach its maximum pressure level? So don't be confused. It says at what temperature will the tank reach its maximum pressure? So the maximum pressure was given to you here. The maximum pressure is 450. All right. Let's set this up with our variables. We're given our equation down here. I'm going to rewrite it. And I didn't give you, I did give you the R values. Okay, so you see your 8.31 or your 0.008. Okay, pressure, volume, N, R, and T. Pressure, max pressure is 450 kilopascals. Volume is 348 milliliters. Number of moles, 1.5. And the question is at what temperature? So we're going to be solving for T. And so actually none of these units are correct in your options. Pretend that they all say Kelvin. This is strange. I don't think this is right. No, I think I did something wrong. Excuse me. So late. I think I did something wrong when I listed these options. I don't think any of these are correct, but let's go ahead and see. That's kind of a large Kelvin value if it is. Let's go back to our R. Our R value, we're given pressure in kilopascals, so we have to use the R value with the kilopascals in it. So we're going to go ahead and use 8.31 liter kilopascal per Kelvin mole. Okay? Plug and chug. Solve for t. So I'm going to just go ahead and divide by r and r on both sides, giving me a new equation. PV over NR equals t. So we have 450 times 348 equals t over 1.5 times 8.31. Okay, let's solve that. 450 times 348 is 156,600 divided by 1.5 times 8.31. 12.47 equals t. So much number crunching. I get a really large number. And I get 12,558 Kelvin. Oh, I know why. Can you find it? I'll give you a second to look. You go, something is wrong here. Whenever your number ends up really big or really small, you gotta find what happened in the units. I see what happened in the units. Your R value has to match all the other units in the problem. So we have liters. We have milliliters. We're working in milliliters and liters. We can't do this. It doesn't equate. What we needed to do was convert 348 milliliters to liters. Okay? There are 1,000. I can do this several different ways. So let me do this. 348 milliliters. We'll use dimensional analysis. There are 1,000 milliliters in 1 liter. So we're going to divide by 1,000. You could equivalently move this decimal place 1, 2, 3 places and come up with 0.348. What that's effectively going to do is we can go in here. Whoops. Those are my boys. We can go in here and we can change this value. So let me use a different color. How about blue for a decimal? And so in here we could do the calculation all over again, or we could just move the decimal place for our answer over 2 places. 3 places, sorry, wait a minute. How about 3 places? Because we moved it 3 places from initially. So now the number seems kind of small. 12.56 Kelvin. 125 sounds good to me, but didn't come out that way. Oh, it would move. Whoops. I'm making everything go crazy here today. Ugh. It should look something like that. Let me make sure what this is. 156. 156.6 divided by 12.47 is 12.55. Okay, hopefully if you found an error in what I've still done, then you can fix it. But I think this might be right, because then we have kilopascals, 8.31, right? Kilopascals in pressure. We have moles, we have Kelvin, and so we're solving for Kelvin. So everything else there should be correct, except for, everything that I did leading up to that. Sorry for the confusion there. Okay, moving on to lesson 11. Lesson 11 was very conceptual, really wasn't a whole lot of practice, but it is having everything to do with temperature and temperature conversion. So in lesson 11, we defined temperature not as the heat in a room, not how warm the room is, but using that term kinetic energy in our definition, we would have to say temperature is a measure of the kinetic energy. I'm going to abbreviate here, of a molecule or a sample of molecules, gas sample. Okay, how fast the molecule moves determines its temperature. Temperature is a measure of that. So the hotter temperatures, more faster moving molecules. Which leads us to question 2. Do substances at a higher temperature have more or less kinetic energy than those at a lower temperature? The ones that are hotter move more, move faster, have more collisions, etc. They're higher energy. What temperature is described by the phrase absolute zero? This is as cold as we can get. That is 0 degrees Kelvin, and nobody's actually reached it. At that temperature, what theoretically happens to the kinetic energy of molecules? They stop. Again, theoretically, because we can't experiment this too easily unless it's like in a very, very cold chamber. Because if our molecules in our body stopped, and if the gas molecules we breathe stopped moving, we would not move anymore. Number 5, any temperature expressed in units of Kelvin is called an absolute temperature. Okay? So if you're asked, please convert this temperature. Oh, we might have one of these examples here. It says, for example, at 90 degrees C, the pressure inside a gas-filled container is 600 kilopascals. What is the absolute temperature of the gas? I would say pressure doesn't matter much here. That's just thrown in there to trick you. Absolute temperature means you are taking that 90 degrees C, adding 273 to it to solve for your Kelvin temperature. And so it's never going to be your degrees C, because degrees C is not a Kelvin temperature, which means it's not an absolute temperature. When you add then, it has to be plus 273. And you can't just convert, like for example, in part B, in option B, it says 90K. You can't just take your original pressure and make it a Kelvin. You have to do that addition of 273 to it to make it Kelvin. So 363. And we went through several of these examples, so you should probably feel confident there. Though we have another one, and we did this example in class. It says carbon dioxide has the greatest kinetic energy at which of the following temperatures? And we're given a couple options in degrees C and then one option in Kelvin. So we can approach this a few different ways. What I'm going to do first is say, well, greatest kinetic energy is going to equal the highest temperature. And I know that. That's the definition of temperature and how temperature works. Temperature is a measure of kinetic energy. The higher the temperature, the higher the kinetic energy, the more movement, the faster we go. Okay? So, just comparing degrees C, we have 50, 30, and minus 10. Clearly, 50 wins out in that set. Now, we have to always compare apples to apples. Either all temperatures have to be absolute, or in general, they have to match. In degrees C, we cannot compare degrees C to degrees K here, because they're two different units. So, it's easiest for me to just convert my degrees C to Kelvin by adding 273, because that's the one I remember all the time, not really subtracting 273. And when I do that, I come out with 323K. So if 50 is 323K and my option A is 273K, then my highest temperature, of course, is B, because 323 is higher than 273. These are the kinds of questions you should expect on the test. You know, what is an absolute temperature? And then based on kinetic energy, which one moves fastest? We're almost there. For regular chemistry, my 1230 class, my 230 class, this lesson 12 is the last lesson that we have studied. Oh, my screen is a little off too. Apologize. Oh, there we go. Okay. Dalton's law of partial pressures. Determine whether each of the following statements is true or false. And highlight your answer. So, gas mixtures behave the same way that pure gases do. True. Remember Randy and his snow clothes? He's the same Randy whether he's in his snow clothes or out of his snow clothes. And his snow clothes don't particularly care about Randy's behavior either. So they're going to be how they are. He's going to be how he is. It doesn't matter if you're together or apart. Okay? Individual gases behave independently of the mixture. True, again, because we make a lot of assumptions of ideal gases. We say they don't interact. So they stay independent. And finally, individual gases contribute to the pressure of the mixture. Also true, because what we find is that Dalton's law is an additive law. It's the total pressure is the sum of its parts. Which leads us to number 2. It says Dalton found that the total pressure of a gas mixture is equal to the sum of the partial pressures of the gases present. I swear I didn't read that ahead of time. I was just blabbing. Write the mathematical expression for Dalton's law. If you're asked to do Dalton's law, you are always looking for P total. If you're not looking for P total, but that's part of the equation, equals the sum of however many gases you have, the pressure of all those gases. And you can go on, you can have 400 different gases, and you can add them all up. As I said, in problems, oftentimes you might see the subscript written in terms of the actual molecule we're looking at. So maybe you have a partial pressure of oxygen, or maybe you're looking at hydrogen gas, or maybe you're looking at nitrogen gas, or maybe you're looking at carbon dioxide gas. So that's just a way to sort of keep track of what your gases 1, 2, 3, 4 are. Okay, Dalton's law of partial pressures, doing an example. There's a couple different examples here. So in our first example, we can use Dalton's law to solve this problem. A tank of gas has partial pressures of nitrogen, oxygen, carbon dioxide equal to 182, 532, and 124. What's the total pressure? Don't forget you have the ability to strategically take your quizzes and tests. So if these are the partial pressures, the total pressure has to be more than each of them. So 532 on its own isn't going to work. 124 on its own isn't going to work, and neither is 182, because those are each partial pressures. They are not total pressures. Okay? Total pressure is going to be the sum of all of them. And so I can work that out for you there. Let's see, what do we have? 11, 12, 13. Whoops. Did I get 738? 182, 124, 532 is equal to 8, 11, 12, 13, 3, carry the 1. Oh, it is 8. 838 kilopascals. Okay? That's the easy Dalton's law to do. This example is going to be a little bit different. This is solving for a partial pressure. Okay? What is the partial pressure of a certain gas? If we have a mixture, Dalton's law is all about mixtures. Argon, helium, and oxygen, we're given the total pressure, 1512 kilopascals. Partial pressure of argon and helium are 150 and 302. So we're setting it up just like this down here. We have P total is 1512. I'm going to make my first gas equal to argon, my second gas equal to helium, my last gas equal to O2. Okay? So we need actually partial pressure then of O2. Argon is going to be 150 and helium's 302. So we're going to solve for that guy right there. And I'm going to come up here. 1512 then equals 452 plus the partial pressure of oxygen. And doing algebra to solve for the partial pressure of oxygen, we just subtract 452 from both sides. 1060. Pressure, we have to check our units, kilopascals. Okay, that's what we got mathematically. Does it make sense? Well, 302 is a partial pressure, so that can't be, well, it can be, but it's not. A partial pressure of oxygen. I guess right here you have to solve. It can't be D, because that's the total pressure. That's really the one you want to rule out. It can be the other two. You have to just calculate it. Okay, phew, I'm tired. We're going on an hour too. It's an intense review, right? I'm ready for bed. Number 6 says use the ideal gas law to solve this problem. Now this is a question I skipped in our lectures with you, like in our live sessions, but I'm going to do it here so that you see it solved this way. It says you have a volume, 12-liter vessel. It holds 5 moles of nitrogen, 2 moles of fluorine, 3 moles of hydrogen. Your temperature is 273 K. What's the partial pressure of hydrogen in the mixture? Okay. So we can use the ideal gas law and the number of moles. This is the other piece. This is the piece that's really important when we're doing Dalton's law using ideal gas, is that we use the number of moles according to how much gas and the partial pressure of that we're looking for. So we would really kind of rewrite this equation as the partial pressure of H2 times the volume total equals the number of moles of H2 times R times T. Okay? Now substituting that in, let's do our things here on the side. We don't know the pressure. That's what we're looking for. The volume is equal to 12 liters. N of just hydrogen is equal to 3 moles. T is equal to 273. And R doesn't matter which R we use, right? Because we're solving for pressure. And judging by the options I gave you, you can use both 8.31 or 0.082. Okay? Let's solve this bad boy. We're going to divide, first and foremost, divide by V total on both sides because it cancels, and then we're just solving for the pressure of hydrogen. This is our new equation, right? So we have 3 moles of hydrogen multiplied by, I'm going to use the big number first, 8.31 times 273, all divided by 12. The pressure of hydrogen equals 3 times 8.31 times 273 divided by 12. 567. And 8.31 is our kilopascal. I didn't write it there. Oh, I've given it to you right there. 8.31 is our kilopascal, so that's what our pressure ends up as. And it looks like we have the answer here, C. But part E says, can both B and C be correct? So I'm going to go ahead and I'm going to highlight this solving in yellow. I'm going to solve it next using this other R value. Okay, so I'm going to say P of H2 is equal to 3 times 0.082. And all things the same, that's going to equal 5.6 ATM. So looks like E is the best answer here. Both B and C are correct. Always remember that if you're solving for P in your ideal gas law, you can use any R value you want, assuming those units are in your choices. That is. Okay? That's enough of that. Now, if you are in my 12:30 class, my 2:30 class, get the heck out of here. Okay? You don't have this schedule for the week. So if you're in my 12:30 or 2:30, it doesn't look like this at all. 12:30, 2:30 class. Review worksheet. Complete it. Submit it today. Take test tomorrow. That would be Friday. I will be finishing up PSSAs. You guys can shut me off. I have to work a little bit longer with my honors section, okay? So if your honors, hang in there. I know I'm at an hour. I'm going to wrap up soon. These lessons are more fresh in our head. I'm just going to try to go through them quickly as a summary. In lesson 13, we talked about Graham's law of effusion. The primary difference between diffusion and effusion is that diffusion is in any space, and effusion is through a small hole. Okay, so what's happening in any space and through a small hole? Gases travel from source, I'm going to call it the source, that is our high concentration, to somewhere far away, far away, like in Shrek, land of far away. That's low concentration. Okay, and the only difference then between diffusion and effusion is that effusion is happening through a tiny little hole, maybe in an experiment where we've capped off an end tube with like a piece of cheesecloth or some semi-permeable material. Okay, so then which travel more quickly? According to Graham, small light gas molecules travel more quickly. That makes sense, because if we're skinnier and lighter, it's easier for us to maybe run down the street. And if we're heavier, it's not quite as easy. Big things don't move fast. Small things do. So that's the relationship then between rate and molecular weight. So this says molecular weight, as molecular weight increases, then the rate of effusion or movement decreases. Okay? And vice versa, of course. If the molecular weight of a substance is low, then the rate increases. The mathematical equation that relates these two things, rate and molecular weight, goes something like this. We have rate of some compound A and rate of some gas B equaling the square root of the molecular weight of B over the square root of the molecular weight of A. Remember, molecular weight is also the same thing as molar mass. So you might see that as MW or you might see it as MM. It doesn't matter as long as you're using it the same way. And I'm just going to point out one more time that these are flipped. Okay, so it's not like a proportion whereas rate A is to rate molecular weight A, rate B to that. It's not, it's flipped. Okay, and that's where most people will make their mistakes here. I'm going to skip question 4 for now because this is taking forever. I would like you to, no I'm not, I'm just going to do it. The heck with it. It says a sample of carbon dioxide gas effuses through a porous container 6 times faster than an unknown gas. Estimate the molar mass of the unknown gas. So we're going to use this equation and my rate A to my rate B. So wait a minute. I said when we do these problems we should be very clear and consistent about what A and B are going to be. So we know one gas here, right? We're going to call A CO2. And gas B is our unknown gas. And we're trying to solve the molecular weight of that. So if A is carbon dioxide, then our molecular weight of A is going to be 12 plus 32. I'm getting that from the periodic table. 2 times 16 for oxygen is 32 plus 12 is going to give us about 44 grams per mole. We do not know, we need to solve for the molecular weight of B. Okay? But we know the rate A to B, CO2 to the unknown is 6 times whatever this is. So it's 6x or x. We're just going to assume x is 1. Or we could use 6x and x and it cancels. Okay, so let's go ahead and do that. 6x and x equals the square root of b divided by the square root of 44. Okay, on the left hand side, x's cancel. We're left with 6. We're going to multiply both sides by the square root of 44 to leave the square root of b alone on the right. So we have 6 times square root of 44, 6.63. Now to get rid of the square root on the right, we have to square it. And that means that our answer is 44. Wait a minute. Did I multiply by 6? Let me see here. 44 square root. No, I didn't. I forgot. Times 6. This should be 39. 39.8. 39.8. Now we need to square that. And that's equal to 1584. That seems awfully large. 6 is CO2. CO2 is on the bottom here, square root of 44. Multiply, cancel. Checking my math one more time. Square root of 44 is 6.3 times 6 is equal to 39. Is the square root times squared. Okay, if somebody knows what I did wrong here, let me know. This is the answer I'm getting, 1584 grams per mole. That's kind of insanely huge, but it could be correct. I don't have an answer key for this, so I believe it's correct. We're going to go with it. After lesson 13, we talked about phase diagrams. So now we're starting to get away from gases. We want to understand how a gas becomes a gas, from a solid or a liquid, how we interchange, how we explain, and so on. This question 1 can go all the way back, and you can answer this perfectly using your answers from question 1 in lesson 1. So I'm going to skip that for now because we have bigger fish to fry, right? We'll revisit this diagram because these are terms that you absolutely need to know, and I didn't give them to you here. So recapping what this is all about. When we go from a solid to liquid, we have a process called, not evaporation. Solid to liquid is called, of course, melting. If ice becomes water, we have melting. And in the course of that happening, we should think about, is energy gained or lost? Energy has to go into the ice cube for it to melt. Okay, so there's energy in. We didn't really focus a lot on the energy part, but bear with me. We're just going to incorporate that now. Energy is gained by the ice cube to become a liquid, because remember, I guess we did do it inadvertently. Our solid molecules are slow moving and kind of rigid, right? The liquid molecules move faster than solids. So if we're talking about kinetic energy, this one is the greatest, has the most kinetic energy. This one is high in kinetic energy. Wait a minute, backwards. This one has the least kinetic energy. This one has some, and this one has the most. Okay? Okay, sorry, back to my chart here. Going from a liquid to gas. Oy, how did that happen? Okay. This is evaporation. Liquid to gas. Evaporation. Also sometimes called vaporization. Okay. Number 3. We go from a liquid to a solid. That's, of course, the opposite of melting. That's freezing. And a gas to a liquid, this is called condensation. Okay. In terms of energy, for evaporation, we have energy gained. So as we go to a more disordered substance, something that's solid to something that's gas, we're gaining lots of energy. And when we reform our more structured molecules, our liquids, our gases, we're losing energy. When we go solid to gas, this is called subliming or sublimation. And when we go gas to solid, this is called deposition. So be familiar with that. Looking at an actual phase diagram, we want to label the phase diagram using the word bank. This whole area in here, A defines an area. That would be a solid area. Okay, crossing that off of my word bank. B, this whole area in here between those two curves, this is called our liquid area. And C is down here, this whole area underneath there, this is called the gas area. So we have solid, liquid, and gas. We need to find also the fusion curve, vaporization curve, and sublimation curve. So let's go with fusion curve first. Fusion curve is going to be right here, D. Fusion describes going from solid to liquid, melting to freezing, freezing to melting. Our vaporization curve is going to be between liquid and gas because that's where our process of evaporating and condensating happens. And then finally our sublimation curve is down here, the difference between our solids and our gases. I don't have a color that matches that. So subliming or depositing, that line is crossed there. So you'll remember that any point along this line describes a melting or freezing point at a certain pressure and temperature. Same thing, every point along this line describes a boiling point, temperature and pressure. And so we can answer questions like this one, where we're given a general phase diagram for some substance, and it says what phase is substance X at a certain pressure, let's say 4 atms, we're going to draw a line straight across here, and 40 degrees C, up and down here. So our intersection point is the one we're looking for. It says what phase is it, and it ends up happening right on top of a liquid, so that substance is going to be liquid at that pressure and temperature. It says what is the melting point of substance X? So at 4 atms, if we look at our 4 atm line again, and now we focus on our fusion curve right here, then we will see that the intersection of the fusion curve with that pressure is going to give us a melting point, and that's going to be about 20 degrees C, it looks like. We're going to do the same thing for boiling point. I'm going to take a blue pen this time. At 4 atms, our line is right here, except this time we're going to be going ahead and looking at the intersection with the vaporization point to get boiling point. So we get that point, and we draw our line down. It's about 55 degrees C. Okay. In addition to finding those points and describing what state of matter we have under those conditions, we do also want to be able to explain what happens when we go from one state or from one set of conditions to another. So in this example, number 9, it says what happens when you increase the pressure from 2 atm to 4 atm at a certain temperature. So let me go ahead and erase some of this. Can I do that? Yeah, how about I do that? Erase my mess. Okay, we had what? We had 40 degrees C, so I'm going to draw my line up. It's about my squiggly line up. From 2 atm to 4 atm. What happens? Well, this is what happened. We went up, right? From this point to this point. So we started as a gas, we ended as a liquid. Start as a gas, end as a liquid. Start as a gas, end as a liquid. That's called condensation. Whoops. So condensation happens when we do that. We start from a gas and go to a liquid. Okay? What happens when you increase the temperature of substance X? at 4 ATMs from 40 to 70. Getting rid of this chicken scratch. We're looking at 4 ATMs again and starting at 40 degrees C and then looking at 70 degrees C. We're looking at this point versus this point. And what has happened is that you went from a liquid area to a gas area. So liquid to gas is going to be vaporization. You cross the vaporization curve, so that's what's happening there, or what we better know as evaporation. Okay, phew, did I mention I'm sleepy? So sleepy. But guess what? We're done. Now, honors, I didn't go over with you lessons 15 or 16 because they should be fresh in your head. You just did them. There really wasn't a ton of information there to go with that. It's mostly talking about intermolecular forces versus kinetic energy. And so you want to just revisit your notes on that for solid, liquid, and gas. If you felt good about most of this, you're going to do fine on the test. Obviously, I've invested in a lot of time for you to do well on this test. Now, I assume if you're still watching that you are in my honors class, and this schedule that I have does apply to you. Okay, doke. So, you should have done all of these things this week, and if you didn't, please get on them soon. Today you are watching the review day. Get that submitted. There should be a Dropbox there. Send me a message if there's not. I have been testing all day, every day. I come home and I have other things to do. Then I get to your lessons, which take me hours all night. I don't mean to have pity here, but I haven't gotten to my K-Mail. I do apologize. I will get there soon. Please complete your test tomorrow. You will not get a message from me tomorrow in a video form. Instead, I will K-Mail you and upload the test slide supports for your exam for Thursday. And then look Friday for another installment for me, hopefully the last one for the week, detailing your Honors Project 1, which has everything to do with gas laws. Okay? I watched this, guys, and I'm afraid I bore you to tears, but I hope this was a helpful tutorial, a helpful answer key to your worksheet, and that those of you who are already confident about this stuff and you're just like, oh, are you ever going to stop talking, Mrs. Grosses? Thank you for your patience, because there are definitely other people who need that level of detail and rigor. Okie doke. See ya next time. Bye.